All right, friends, this is what we did in class on Wednesday, March 29th. The day before we did this packet, we used BCA tables to predict how much product can be made from various amounts of reactant. That's what part one of this video series was about. That's the first part of stoichiometry, is predicting amounts of products from a given amount of reactant. This time, today, in this video, we're doing the opposite. We're going to predict how much reactant is required to make a certain amount of product. So it's the same thing. It's the same kind of thing. We're still using BCA tables. It's still stoichiometry. But the steps for using the BCA table, it's a little bit different. We got to just shift our thinking a tiny bit. And I'll show you what I mean here. Number one asks, how many molecules of nitrogen and hydrogen are required to produce 18 molecules of NH3? So now, originally, we would start by putting numbers here and there, right? But on this one, that's going to be our final answer, right? Because we want to know how many we need to begin with if we want to end with 18 molecules of NH3. So the first number that I'm going to write is actually 18 molecules. And I'm going to put it down here because we want that many molecules at the end. Well, in order to have 18 molecules at the end, I got to make 18 molecules in my change row. And we know also that I started with 0. Okay. Now, this is the step that's really critical because now I need to ask myself the question, how many times, this is the same question I ask myself every single time, how many times do I need to run this reaction? How many times do I make the recipe in order to produce these 18 molecules of ammonia? Well, I can notice here that each time we run the reaction, each time we make the recipe, we make 2 molecules of NH3. So if I want to make 18, then I should do 18 divided by 2. To give me 9 times, right? So that 9, I'm going to pull it up here. And that's going to be 9 times that we do this whole thing. If I'm doing the recipe, making the recipe, doing the reaction 9 times, now I know how many molecules of reactant I'm going to need to spend in order to make that much product, right? So I can distribute this 9, just like we were doing in the last video. I can distribute this 9 to the coefficients that are remaining, and I can multiply that together to make my change row, or to fill in my change row. So 9 times 1, I got to use 9 molecules of nitrogen if I'm going to do this reaction 9 times. 9 times 3 is 27. So I got to use 27 molecules of hydrogen in order to make this reaction 9 times, or do this reaction 9 times. Now, the rest of it is really just like kind of a logical thinking, because now if I'm using 9 molecules of nitrogen, well, I got to have 9 molecules of nitrogen to begin with. Otherwise, I can't spend them. Same thing over here. I got to start with 27 molecules, or at least 27 molecules, if I want to use 27. Now I do my subtraction just to finish this up. I'm left with no reactant, and I've spent all of my reactant to make 18 molecules of ammonia. Cool. So now I have answered the question. Actually, not yet, because I have not circled my answer. This is really important, guys. On these questions, like on your quiz and on your test, you need to make sure that you're actually answering the question. This table does not answer my question on its own. So if it says circle your answer, if you don't circle your answer, then I don't know that you know what the table means, right? I don't know that you know what B means, or C, or A. Before what? After what? If you don't show me that you understand that this is the answer to the question, how many molecules of nitrogen do we need, then I don't trust that you understand what you need to understand about stoichiometry and BCA tables. You see what I mean? So you need to circle your answer or write it in the blank or whatever. You need to make sure you answer the question, basically. Okay, let's go on to number 2. You can probably do this one yourself, so pause the video here and give it a shot. Here we go. Just like in number 1, we're starting with how much we should be producing. So I'm producing 20 molecules of water. I'm going to put that down here. I know right off the bat that that means that I need to make those 20 molecules of water, and that means that I'm starting with 0. Just like before, the next step is to figure out how many times do I run this reaction in order to produce those 20 molecules. Well, each time I run the reaction, I make 2. So if I do that division, then I'll get that I need to do this reaction 10 times. So I'll pull that 10 up here. Okay, now I can distribute the 10 to fill in the rest of my change row. I'm going to use 20 molecules of hydrogen, and I'm going to use 10 molecules of oxygen. In order to spend it, I got to have it, so we know what we're starting with as well. And then we do our subtraction. Easy peasy. I'm going to make sure that I'm answering my question. It's asking how many molecules of H2 and O2 are required to produce. Boop, boop, boop. There it is. Oh my God, that's wrong. Sorry, it's this one. 20 molecules of hydrogen and 10 molecules of oxygen. That is what is required to produce 20 molecules of water. Let's go with that for a sec. Let's say that I circled this on my quiz. I would get the question wrong. I would not give you credit for this. Because you don't answer the question correctly. If you circle the wrong thing, then it demonstrates to me that you don't know what the table means. And that's a huge, huge problem. I don't care necessarily that you know exactly how to use the BCA table. I'm giving you the BCA table. I'm showing it to you as a tool to use, right? But the point is to be able to predict how much reactant is required to produce a certain amount of product. Like, that's what I need. That's the skill I need you to be able to do. Not fill in the BCA table. You got to know what it means as well. So you got to do that if you want points on the test, points on the quiz. Number 3, again, you can give this one a shot yourself. And here we go. We're producing 14 molecules. You're probably getting the hang of this by now. Don't skip through the rest of the packet, though, if you're like, this is easy, because there's one other kind of problem, and it's number 4. You'll see that number 4 is a little bit different. But I'll just fill this out now. One thing here, this is 4 phosphorus atoms, right? Atoms of phosphorus we're dealing with, not molecules. The reason I know that it's an atom and not a molecule is because there's no subscript down here. It's not P2, it's not P4, so it's not multiple atoms bonded together. It's singular atoms, right? So 4 phosphorus atoms looks like this, where they're not bonded to each other. They're just 4 atoms just kind of floating around in space, or it's actually probably solid phosphorus. Anyway, 28 atoms of phosphorus being used. 7 times 5 is 35 molecules this time of oxygen being used up. In order to spend it, I got to have it. Do my subtraction. Circle my answer. This is what is required in order to produce those. That's going to be this. That's my reactant in the beginning. And there we go. Just, by the way, you cannot just remember that you always circle the thing in the upper left, or because you need to read the question. Sometimes I'll ask you different things, okay? You got to pay attention. You got to pay attention to the question. And I'll remind you of that on the quiz as well. How many molecules of CO are needed to fully react with 8 molecules of O2? So this one's a little bit different. We have some different wording here, a new phrase, fully react. We'll break that down in a second, but for now, we know that we're starting with 8 molecules of O2. I'm not producing 8 molecules of O2. I'm reacting with those 8 molecules of O2. So that actually tells us what we start with in this case. We start with 8 molecules here. Now I can, once I see the phrase fully react, this fully react means that I'm going to use up all of my reactant. So I'm going to use all 8 molecules of my oxygen. 8 minus 8 is 0. There's going to be no oxygen left. Fully reacting with 8 molecules of oxygen. Okay, and the question is how many molecules of CO. So we need to fill out the rest of our other reactant and our product as well. The way that we do that is, again, we divide by our coefficient up here. So divide by 1, and that's to figure out how many times do I need to do this reaction in order to use up all 8 of those. Well, 8 divided by 1, of course, is 8. So I got to do this whole reaction 8 times. Now I can distribute my 8 to each of my coefficients in order to fill out the rest of my change row, the rest of my C row. Okay, so 8 times 2, I'm going to use 16 molecules of carbon monoxide, and I'm going to make 16 molecules of carbon dioxide. In order to spend it, I got to have it. Once I spend it, I don't have it anymore. I start with 0 products because that's before the reaction occurs. After the reaction happens, I got 16 molecules. There we go. Circle how many molecules of carbon dioxide are needed to fully react. That's this number right there. There we go. All right, so number 5 here. Why don't you give this one a shot before I show you how it works out? You can pause the video here. All right, let's go. Here we want to know how many molecules of methane, this is methane, how much methane is required to fully react with 150 molecules of oxygen. So that's telling us how much oxygen we are starting with. So I'm going to put 150 molecules right there. I know that I'm fully reacting those 150 molecules, so my change row should be minus 150 because I don't want any left over. I want to react all of it. Another question that I ask myself is, in order to react all 150 of those, how many times do I have to do the reaction? Like what number do I put right there? And the way that I get that is, remember, I take my change row and I divide it by the coefficient in the chemical equation. It's going to give me 75, so I know that this whole thing is going to happen 75 times. If the whole thing's happening 75 times, then I can use that information to figure out how much methane we're going to use and also how much product we're going to make as well. And we do that by distributing that 75 to each of my coefficients in the chemical equation. So 75 times 1 is 75. I'm going to use up 75 molecules of methane to do the reaction 75 times. And I'm going to make 150 molecules of water, as well as 75 molecules of carbon dioxide. Coming back over here, if we want to use 75 molecules of methane, then we got to have it in the first place before we can use it. And if we use all of it, then we're going to be left with none in the end. Similarly, over here on the product side, we don't have any molecules of product before the reaction occurs because it's before the reaction, right? And then once we make 150 molecules, that's what we have at the end. We got 75 molecules over here. So now I filled out the table, but I'm not done until I circle my answer, box my answer, whatever the question's asking me to do. This says, I want to know how many molecules of methane are required. So that's going to be this number right here. 75 are required in order to react with 150 molecules of oxygen. So I'm going to circle that answer. And it's also asking how many molecules of water will be made. That's 150, so I'll box that number right there. Next. Again, give this a shot. Pause the video here. And now here we go. How many molecules of hydrogen sulfide and oxygen are needed to produce 16 molecules of sulfur dioxide? So now I'm producing 16 molecules of sulfur dioxide. This is like the first 3 that we did on the previous page. Producing 16 molecules of sulfur dioxide. In order to do that, we're going to have to run this equation 8 times. Because each time we run the reaction, we make 2. So if we want to make 16, we got to do the whole thing 8 times. If we're doing the whole thing 8 times, then we can figure out how much H2S we're going to use and how much O2 we're going to use as well by distributing that 8 to each of these coefficients here. So I'm going to use 16 molecules of hydrogen sulfide, and I'm going to use 24 molecules of oxygen. In order to spend the reactant, we have to have the reactant in the first place, so then we can put our 16 or 24 in the before row, and then, of course, we can have 0 molecules after. 24 minus 24 is 0. We also want to know about how many water molecules are going to be made. So before the reaction, there's none. If we're running the reaction 8 times, we distribute that 8 to the coefficient of 2 to get 16 water molecules produced. 0 plus 16 is 16. And there we go. There's my boxed answer. The circle is, I'm supposed to circle how many molecules of each reactant are used, so I'll circle this. Remember, if you don't circle the right thing, I can't really give you credit for the question, because the whole point is to use the BCA table to answer the question being asked. If you just write out the BCA table but you don't know what any of it means, that's a problem, right? And I can't give you credit for knowing how to do stoichiometry, because stoichiometry is like actually doing the conversion or getting the answer, I guess. You can't just fill in the table and then say that you know how to do stoichiometry. There's more I don't want to do all of these. We're gonna skip 7 and 8. Give those a shot. If you get stuck, if you get confused, come in for help on those. There should be enough questions in this video for you to get the hang of this already, just from what I've done. And that's good practice for you anyway, so you do it. How many molecules of hydrazine are needed to fully react with 32 molecules of hydrogen peroxide? Hydrazine. This one is hydrazine. And this one is hydrogen peroxide. We want to know how many hydrazines are needed to fully react with 32 molecules of hydrogen peroxide. So we're starting with 32 molecules of hydrogen peroxide, and we're going to use all of it. In order to do that, how many times do we need to do this reaction? 32 divided by 2 is 16. So we do the whole thing 16 times. 16 times 1, we're going to use 16 molecules of hydrazine in order to do this reaction 16 times. We're also going to make 16 molecules of nitrogen. To get the number of water molecules used, we do 16 times 4 to get plus 64 molecules of water. And then we can just fill in the rest. Okay, number 10 here is a little bit different from the other ones in the packet, but it's just like the ones from the first packet that we did, so the packet from Tuesday. This is just to remind you that there are like 2 different kinds of questions, or really 3 different kinds of questions. I don't want you to forget how to do these just because we started doing something else. So here we have 4 molecules of acetylene, that's acetylene, sorry, and 15 molecules of oxygen. That's what we're starting with. And we want to know how many molecules of carbon dioxide can be made. Well, whenever they give us amounts of 2 different reactants, we need to do our division for both of them and then take the smaller number again, just like we were doing on Tuesday. So 4 divided by 1 is 4, and 15 divided by 5 is 3. So we're going to take the smaller number here, take 3, pull it up here. We're going to do this whole reaction 3 times. We're following the recipe 3 times. Now I distribute the 3. 3 times 1 is 3. We're going to spend 3 of these, have 1 left over. 3 times 5 is 15, so we're going to spend all 15 of these oxygen molecules, end up with 0 molecules. We're going to make 12 CO2s, and we're going to make 6 H2Os. Of course, no product to start out with. And in the end, we'll have this much of each. Here we go, completed BCA table, just like that. We need to box how many molecules of carbon dioxide are being made. So that's this. And circle what will be left over. 1 molecule of acetylene left over, just like that. In number 10, this one is, you can still answer this with the BCA table, but before you can do that, we need to figure out what the coefficients are in this chemical equation, right? Because like look at number 10 right above it, right? I gave you the coefficients, but we did like, what was it, like two and a half weeks or something on balancing chemical equations before the break. So that was when I gave you the blanks, and you had to figure out, okay, how many oxygen molecules do we need to react with one molecule of acetylene, for instance, right? And so that's a skill that you should still have. We should still know how to take this unbalanced chemical equation and move the bingo chips around in our head, right? Or whatever method you use, and to get this balanced chemical equation. I can show you real quick how I balance this so you can have a nice refresher. What I do is, with combustion reactions, I always do it in this order. I balance my C's, and then I balance my H's, and then I balance my O's. That's just the easiest way I have found to do combustion equations specifically. So I'm going to balance my C's first. I notice that I have 3 carbon atoms over here in 1 propane molecule, but I know that all of these carbon atoms are going to end up as parts of carbon dioxide molecules, because that's the only place that C is on the right side of my equation. So I know then that I need to make 3 carbon dioxide molecules, at least. Now my C's are balanced, so I'm going to do my H's now. Same thing over here. I got 8 H atoms, hydrogen atoms over here, and I know that all of my hydrogen atoms are going to end up in water molecules, because I need to obey the law of conservation of mass, right? I can't have those hydrogen atoms disappear. So if I got 8 atoms and each water molecule takes 2 hydrogen atoms, then I can make 4 out of the 8 that I have, 4 water molecules. Now my H's are good. Now let's check my O's. I got 6 oxygens over here, and I have 4 oxygens over here, so that's a total of 10. If I need to make this many product molecules, right, I need more oxygen atoms to play with, right? Because as it is, I only have 2, and I need 10. The way that I can make that 2 into a 10 is by putting a 5 right here. If I start with 5 molecules of oxygen, then I have enough oxygen atoms to finish those product molecules that I need to make. Okay, so that's a quick refresher on balancing. So now it's balanced, right? My C's, my H's, or my O's are good. 1, 5, 3, 4 is how this balances. Now I can do my BCA. Just like we did before, but this time we figured out the coefficients instead of me giving them to you. Okay, this says we have 3,000 molecules of propane. C3H8 is propane. If you didn't know that, you could have figured it out by process of elimination because you know what the other ones are. So that's 3,000 molecules to begin with. And we want to know how much oxygen we need to fully burn all the propane. Well, fully burn is the same as fully react. So I want to use up all of my propane. No propane left. In order to do that, we got to ask ourselves, okay, how many times are we going to run this reaction? So you can do 3,000 divided by 1, because that is the coefficient on my balanced chemical equation for propane. So now I know that I'm doing the whole thing 3,000 times. I can distribute that 3,000 to my 5, my 3, and my 4 to figure out how much oxygen I'm going to use. I'm going to use up 15,000 molecules. I'm going to make 9,000 here, and I'm going to make 12,000 H2O. And there we go. So we got our answer. We need at least 15,000 molecules. We're going to make 9,000 of these. And we're going to make 12,000 of these. 0 product to start with, as always. There we go. That's a completed chemical equation, and I circled my answer already. So, well, I'm almost good. How many molecules of carbon dioxide will be made upon the combustion? Carbon dioxide is right here. So I'm going to box this number. There's my answer. Full points on the quiz. Number 11. I'm not going to go over number 11 in this video because I might make another video for it, but it's too much to do in this video right now. This is just kind of a nice challenge for those of you who want that. The situation is that you are dying of thirst and you don't have any water to drink. All you have is a bunch of methanol. So the question is, you know that like you can do a combustion equation or a combustion reaction, sorry, on methanol. You can burn it to make water vapor, and then you can collect that water vapor and turn it into liquid drinking water. So you need to write the combustion equation for methanol and then figure out how many methanol molecules we have to burn in order to make this many water molecules, right? So it's a huge number. And it's kind of fun, I think. And there's some questions about the mass of so many methanol molecules. That should be methanol, not ethanol. And then there's a density question and blah, 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 blah. So if you do all the math, I think it comes out to 960 water bottles. So if you can get that answer, then you're in good shape. That's just a fun question, though. You don't have to do that. Nothing like that's going to be on the test or the quiz. Okay, cool. This video is going to be posted soon. I haven't made it yet, but this is the video for Thursday on the notes that we did here, and here are the answers. If you didn't write those down in class today, then you can, here they are. Video on this will go up soon. I don't know if it'll be up today, but it'll be up definitely by the end of the weekend. I know you might be thinking, what's the point? The quiz is tomorrow. But the stuff on the test is going to be the same as the stuff on the quiz, right? So this is still be useful for you after you take the quiz, because you'll have a chance to like retake it, sort of. Okay, so that's that. I'll wrap this up now.